Alrighty. Today we're going to talk about how we name compounds. And naming compounds is going to be an important thing for us because we're going to see that if we have some sort of system of being able to talk about what elements are within a compound, we'll be able to easily identify them. And from that, we can kind of generate the chemical formula when given a name, or vice versa. So we're going to see that these kind of come in two different flavors, as it were. We have ionic compounds, which are going to be made of a metal plus a non-metal. And then technically either can be substituted by a polyatomic ion. And so we're going to see that that's an option there. And then we're going to have ones that are called molecular or covalent. And those are going to be when we have multiple nonmetals together. So we're going to kind of start off by learning the rules for naming ionic compounds. Thankfully for us, the rules are quite straightforward. The only thing that kind of gets tricky here is some students tend to, apply the right rules to the wrong compounds. So we're going to see that metal, non-metal ones have their own set of rules. We're going to have a different set of rules for non-metal. And then later on, afterwards, we'll talk about acids. They're going to have their own kind of naming system. Those are going to be made of hydrogen ions and an anion. Either polyatomic or a non-metal. But let's talk about ionic compounds first. So ionic compounds these ones are made of ions, of course. Remember that ions mean they are charged. So we're going to have positive ones and negative ones. Typically, especially in this class, we just have one cation and one anion. And by that I mean one type, not necessarily one, like just one cation, like one sodium ion, but I just mean that sodium will be your cation here. And that your anion can be whatever your anion happens to be. And so we kind of have our, most famous one, of course, being sodium chloride. We're going to see that this is made of Na plus and Cl minus. And if we're to look at the names of just these two, this is sodium, and this is the sodium ion. There's not actually a new, we don't change the name at all, we just throw the word ion on afterwards. And if we look at chlorine, if we have it just by itself, it is chlorine, same name as the periodic table. But when it's charged, we call it the chloride ion. And we're going to see that non-metal anions end with "ide." So we're going to change the ending of our anions to make them end with "ide." So we're basically going to just cut off the last syllable, whatever it is, and replace it with "ide." Let's just take a look at a couple of those. How about this? This, of course, is oxygen. And if we make it into its ion, that is oxide. We have hydrogen. That can become hydride. Let's see, how about selenium? That becomes selenide. Right now I'm kind of assuming that you guys have the kind of periodic table kind of thing in your back of your minds, where you'll see that's where I'm getting these charges from. Like oxygen and selenium are both in group 6 or 16, depending on your periodic table, and they're going to make 2- ions. That's why I'm getting those charges. And let's just do, how about one more, phosphorus. Phosphorus will become phosphide. So notice again, all of these end with that "ide" ending. And that "ide" ending is what tells us that they are negative ions. Okay? Any questions on that one? On that kind of idea? Alrighty, so the name for an ionic compound just like sodium chloride is kind of our example, we're going to see it's going to be your cation, and then a space, and then your anion, and then whatever ending it has. So if it's, let's say it's this particular one, that's made of these two particular ions. This one's name is just calcium. We don't change the name for the positive ions. And this one is going to be sulfide. So we would say that the name of the compound between them is calcium sulfide. Hooray. Not terribly difficult there. So if you can identify the elements, you'll be able to come up with a name for that compound. Now, thankfully, this all works because for every particular compound, there's just one name. And so we're going to see that anytime we are just putting calcium and sulfur together in an ionic compound, they will only ever form calcium sulfide, which has this formula. We'll talk about how to get the formulas in just a little bit, but for right now, we're just focusing on the naming. We'll worry about the next, or the going backwards in a little bit. Oops. All right, how about this one? Notice also in the formula that the positive one always comes first. So that's another component of this naming. So this is going to be made of these two ions. So, of course, hydrogen can go plus or minus, but we know it's minus in this case because it's combined with a metal. Potassium is a metal, takes a charge of +1, so hydrogen will naturally, therefore, go to the minus side. If we have hydrogen with something else, maybe it can be positive. But for ionic compounds, typically hydrogen will be negative, especially if it's combined with a metal. So this will be potassium. And then H- is hydrogen, but we change the, we get rid of the gin part, and we replace it with the ide. ending, so this compound would be called potassium hydride. Alright, hopefully so far nothing too crazy here. We're going to see we can also throw in polyatomic ions. But first, let's talk about how to come up with these formulas based on the ions that you're given. This is a process we call charge balancing. And we use it to make sure that our ions will balance each other out. For all ionic compounds, actually all compounds in general, are neutral. So there's no overall charge for any compound. So if we wanted to make a compound between these two ions, their charges are not the same, right? So we have to balance them out. The way we do this, there's a couple of methods. One of them is finding the least common multiple between them and using that. So the least common multiple is going to be just like, okay, how many, kind of guessing and checking, how many of these can I fit together? You can also kind of just multiply them together. We have a +1 charge and a -3 charge. If we just multiply those numbers together, we're going to see that we want a charge of 3 for each kind of component. And that would be our kind of least common multiple between them. So if we think about that, if we want them to both have a charge of 3, well, N already has that, right? We don't have to worry about that. So how do we make it so that lithium will end up having a charge of 3+? Well, how we would do that, lithium can only ever be 1+. We can't change its charge. So what we can do is just have 3 lithium ions there. And as a result, overall, let's see if I can do this. I'm so bad at brackets. That would be 3 positives. That one's not too bad. And overall, that one's 3-. That means these are going to be balanced out. And we would write this compound like so. We have the subscript telling us there are 3 lithium ions per 1 nitride ion. So that's what the chemical formula is telling us there. Right, another way to do this is a method called crisscrossing, where we take the charge of the ions and make it into the subscript. So if we take that 3 from nitrogen down and put it with lithium, we get Li3. And if we take the 1 from lithium and put it with nitrogen, I mean, we technically get a 1 there, but we don't ever really write 1s. We just leave it blank. We would get the compound that way as well. So you can use either way. You can kind of crisscross the charges, or you can do the least common multiple thing. This one is technically probably the more like, what's the word? Safe way? Crisscross is much faster though. So, but sometimes you just have to keep a couple things in mind when using the crisscross method. And we'll see what those might be in a second. If we take a compound between calcium and oxygen, this is going to be the example of where crisscross could potentially have an issue, but it's an easily corrected issue. If you use least common multiple, you say, okay, you know what, they're the same charge. So I only need one of each. CaO, done. If you crisscross, you get Ca2O2, which is not something that you want to have. If your subscripts can be simplified, you've got to do it. So if they're both the same, or if they're both even numbers, or for example, you have to reduce them to their smallest ratio. So because this is 2 and 2, we would end up reducing this to CaO. All right. Any questions on that one? Okay. Let's go ahead and look at this one then. How about we do the compound between these, barium and phosphorus. If we look up their charges on our periodic table, find where they are, we'll see barium makes 2 plus, phosphorus makes 3 minus. If we do the least common multiple, that's going to be 6, right? We would just multiply the two together. So we want each of those to have a charge of 6. So that means in order for barium to have a charge of 6, we need 3 bariums and 2 phosphoruses. Just so you can see here, we have 3 times 2 plus, that's 6 plus overall. And 2 times 3 minus is 6 minus. And so therefore we would just rewrite those as subscripts, like so. Of course, you can crisscross instead. And you would get the same answer. So whichever kind of method you like to use, go right ahead. But we're going to see there's only one kind of compound we can make between a metal and a non-metal, ionically speaking. All right. By the way, we would call this barium phosphide, of course. We have the barium ion and the phosphide ion. Just put those together. Positive one first, and we win. Hooray! Alrighty. Any questions on that one or anything else we've done? Alrighty. Is there a reason why positive is first? That's just the convention. We always write the positive one first. Typically with any compound, we will write them in order of least electronegative to most electronegative. Again, this is just the convention. We'll learn about electronegativity next chapter, 5b. But that's kind of the way we do it. However, the easier way for us to do that is just we do the positive one first. So, hooray. And that's just kind of the way it is. Chemists like to think positive. Who knows? Cool. All right. So, let's see what happens when we adding in polyatomic ions. Okay, so there's that big old chart of polyatomic ions that's on Canvas and in Discord for you guys. You'll want to start learning that, memorizing it if possible, so that these things can come quickly to you guys. Let's say that we're going to put together these two. We're going to see the process of charge balancing is exactly the same when we have polyatomic ions versus monoatomic ions. And the naming is going to be exactly the same as well. However, that's going to take into consideration the fact that you'll have to know the names of these polyatomic ions. Of course, we know that's sodium, the sodium ion. There. If you were to look up on your polyatomic ion table, you'll see that this is the chloride ion. And just like before, if we put those together, we're just going to put the names of them together as well as sodium chlorate. And we're going to see spelling is going to matter here because if you had sodium chloride, that does not have these 3 oxygens. Sodium chloride just has the monoatomic chloride ion. And just to make things worse, a lot of these ions sound similar to each other, so just beware of that. Here, of course, again, we have the sodium ion. But this time, we have chlorite, the chloride ion. So all of these ions have specific names, which you're going to have to use. And so putting these together, we will get sodium chlorite. So spelling definitely matters here. That's 1 letter away from sodium chloride. You can eat sodium chloride. It tastes lovely. It's salt. If you eat sodium chlorite, you die. So all it takes is 1 letter, right? So be very careful with spelling these names. All right. Hopefully so far so good. Alrighty, let's look at this one now. Alright, if we are going to charge balance this, we can use crisscross method, or we can use least common multiple. Either way, we'll see that we're going to end up with 2 hydroxides and 1 calcium. So we would want 2 hydroxides there to balance out the calcium. Notice if we write it like this, this means 1 calcium, 1 oxygen, 2 hydrogen. However, if we look at what we've kind of just drawn up here, we have 1 calcium, 2 oxygens, and 2 hydrogens. That's obviously a difference, right? We're going to see that this is going to be a not good way of describing this. What we actually will do is use parentheses here. And so we're going to see when we have multiple polyatomic ions, we use parentheses to indicate that. So we're going to use these parentheses here to indicate that we have 2 hydroxides. Because if we just put that 2 outside the H, that does not mean the same thing as what we're trying to say. So we're going to see that we want calcium hydroxide there, with the OH in parentheses. By the way, since I just said it, that name, of course, is calcium hydroxide. It's just the name of the 2 ions put together. You can make things a little bit more fun. How about this one now. Let's do crisscross on this one, why not? Got another problem here. We do not have 42 oxygens in this case. I have forgotten our parentheses. All right, so make sure that you put your parentheses in if you ever have multiple of a polyatomic ion, no matter what it is. All right, so it's going to be important for us also to distinguish these two numbers. This 4 is part of the polyatomic ion. And we must never change this. If we're going to have phosphate, which is what that PO43- is, if we're going to have phosphate in a compound, we must never change that. We can never change that 4. If we do, it becomes a different ion, and it's going to have different properties. However, this 2 outside here is the subscript from charge balancing. And we could reduce this if necessary. If we had, for example, aluminum phosphate, and we did our crisscross, and we end up with this, yeah, we can go ahead and reduce those 3s. That's okay. And in fact, you have to do that. These 3s we can reduce. We can reduce those down to AlPO4. That 4, though, we can never change. All right, so it's important for us to distinguish between subscripts that are part of the polyatomic ion and then subscripts that are from charge balancing. All right, so again, this is going to really be benefited if you memorize your polyatomic ions. You'll be less likely to make mistakes with it if you do so. All right, if we were to name these, by the way, that's the strontium ion and the phosphate ion. So we would call this one strontium phosphate. So as you can already see, if you have memorized the names, this will go much faster than if you have to go on the table and search for PO43- to find its name. So I don't know, I feel like a broken record. I've said that like 15 times. This one would be named aluminum phosphate. Alrighty. Sometimes we have polyatomic ions that are positive. There's not too many. There's just a few of them. But they exist as well. They could replace our metal instead. If we had, for example, this compound, we're going to be able to name that as well by understanding that this is a compound made of 2 polyatomic ions. We have this as our cation, and this as our anion. And guess what I'm going to say? A lot easier to recognize if you've memorized them. I feel like I'm a pusher. Pushing polyatomic ions on you guys. Anyways, name of these are ammonium and nitrate. We put those together, the compound is ammonium nitrate. used in fertilizers, used in explosives. Uh, Something you've probably heard about. I think there was the explosion in where was it? Oh, I can't remember. Can't remember it, but there was that explosion a couple months ago in one of those cities in the Middle East. What was it? Well, whatever. It was ammonium nitrate that had exploded, and so now you know its formula. Congratulations. And I'm gonna be thinking now the rest of the day what the heck that city was. It was Lebanon. Lebanon's a country, isn't it? Uh, so could be somewhere in Lebanon. Yeah, that sounds about right. Hmm. Can't remember. But yes, sounds right. Good enough. So yes, in Lebanon there was that storage of ammonium nitrate blew up. Uh, Hooray. Well, not hooray. That's a very tragic thing. But now you know its formula. That's the hooray. All right, let's see. What else can we do here? How about... Let's just do a couple of them and see what we can do here. Okay. So here's a couple of compounds. Ionic compounds, of course. We can identify the fact that they're ionic because we see that each of these has a metal in it. And then we can see that we also have either polyatomic ions or nonmetals. Alrighty, so naming these is not hard. It just comes down to figuring out what the names of all of them are. So, Ca is calcium. And we would have to look up what the C2H3O2 business is. And we would see that that is acetate. And so the name for this compound is just calcium acetate. Very easy. Just name each of them in order. The next one would be silver sulfate. And then aluminum chloride. And finally, sodium iodide. It may be beneficial to you to indicate what the ions are that make up these compounds. That may help you. For example, this one is made of aluminum and chloride ions. It may be beneficial for you to figure that out. Just in good practice, because we're going to see once we throw transition metals into the mix, it's going to be important that we figure out what the ions are. For sodium iodide, of course, it's made of these two. Silver sulfate is made of these guys. And then the last one, oops. Oh no. Is made of these two. Alrighty. We can see we can kind of go the opposite direction. How about zinc sulfite, ammonium chromate, and how about I don't know, lithium perchlorate. This one's a little bit more tricky because we're going to have to potentially do some charge balancing once we figure out what all the ions are. And so in the interest of time, I have those for you. But if you have the time, I would pause the video and see if you can figure out what all of these ions are yourself as practice, and go from there. But in the interest of time, I'm just going to go ahead and write them all out. And then, okay, here we go. So if we're going to charge balance all of these, or we can crisscross, we'll see we need 2 fluorides to balance out the barium. Or if you crisscross, you'll get the right answer, BiF2. For zinc sulfite, they have the same charge, so we can just put them together. No problem. Ammonium chromate, if we crisscross, we see we're going to need 2 ammoniums, or if we use least common multiple. If we need 2 ammoniums, we have to use the parentheses. All right, we cannot write N2H8. We can't write NH42. We have to use parentheses NH4 parentheses 2. And then the chromate after it. And then for lithium perchlorate, they have the same charge, so we don't have to worry about that. Just throw it all together. Right, you are going to have a ton of homework on this. Hundreds of problems. Because it's a very important skill. Perhaps the most important. No, dimensional analysis. The second most important skill that you'll learn in this class. Yes, I have some tips for you guys. I would just Google stuff. There's probably a bunch of Quizlets that you guys can use as like some like practice. Let me go ahead and pull it up. Not Quizlet, but the like the actual chart here. Let me pull it up real quick. I'll show you some patterns that might help you guys out. Where does that go? Here it is. Okay, so if we switch over here. Is this going to be? No, I have to make a new one. All right. Going to our polyatomic ion table here. If you memorize the 8 form of a lot of these particular ions, you'll see that I have your little cheat sheet kind of up here. If you've memorized the 8 form, you can figure out the ite form and the hypoite form. We're going to see that it's just one less oxygen to go from 8 to ite, and again another less oxygen to go to hypoite. So we see that all of these have this ClO something with a minus charge. The charge isn't going to change, it's just the number of oxygens here. So if you can memorize the 8 form for all of these ions that have 8, you can get the ite by just removing an oxygen. And we're going to see that a lot of these will kind of have that same idea, where they're going to have an 8 form where you can manipulate it. So this is going to be kind of a big hint for you guys on that. However, some of these unfortunately don't have any sort of pattern here, like permanganate. Unfortunately, there's not really a nice way to learn that. Notice that if you look at where these are on the periodic table, chlorine, bromine, iodine all normally take -1 as their charge. You're going to see that their polyatomic ions also take that charge. Sulfur takes a -2 charge typically. Why is hydrogen sulfate not per hydrogen sulfate? Well, so the difference between sulfate and hydrogen sulfate is you've just put a hydrogen in front of it. There's no other difference there. So just putting hydrogen sulfate is enough. There's no need to have extra stuff. Well, the number of oxygens is still the same. So we still have 4 oxygens in each one. We've just thrown a hydrogen on. If we were to throw an additional oxygen, we would call it persulfate or something. If we had SO5 2-, that would be persulfate, following that pattern. So hopefully that answers that. I, of course, did not come up with these names, so this is just the way that these are done. So, flashcards might be a good way to do it. Or, go online, find some Quizlets. That may help you out as well. All right. So, that's kind of the only tips I have for you. Yes. So, unfortunately, if we look at, chlorate, bromate, iodate, yeah, those all have 3. But phosphate, it's 4. Sulfate, it's 4. Carbonate, it's 3. Unfortunately, the 8 form doesn't mean 3. It's a comparison between ite and 8 that has a difference of 1 oxygen. So it would be nice, of course, if this was carbonite instead with 3 or something, or if these were all consistent that way. But unfortunately, that's not the way it is. So all the 8 forms, if you memorize them, they will have different numbers of oxygens. But once you know the 8 forms, then you can get the ite forms from them. So unfortunately, yeah, you're going to see that even if these have ites and 8s, they can have different numbers of oxygen. But if you're comparing the same kind of base, like nitrate and nitrite, that's where the difference is. Cool. Okay, yeah, happy to help there. Alrighty, cool. Let's go away from that. Alrighty. So, yes, that's just, again, something that's going to take time and practice. And in doing the hundreds of problems for your homework on it, you will have plenty of practice with kind of doing this. You'll end up memorizing some just as you go, but of course, it will probably take more practice than even the hundreds of problems. So, hooray. You think I'm joking, by the way. No, there will be hundreds of problems. But you'll see these are not very long problems. They are pretty quick. So, I'll probably put that up for you guys, but it's not going to be due this weekend, of course, because we've only just started this topic. So, yeah. Yes, indeed. Not hundreds of dimensional analysis. Well, that would be nice, though. But that would be very boring, I think. It would get pretty stale pretty quick. At least these are fast. So, okay. So variable charge metals, typically those are going to be your transition metals. Most transition metals, in fact. Will have variable charges, meaning they can go various different charges. That cheat sheet I gave you has common charges for some of these. You'll see that a bunch of the ones in the transition metal block have multiple charges. And while some common ones are written there, that is by no means the only ones. So chromium absolutely forms more than just +2 and +3. Absolutely. So +4, +6 are pretty common with chromium. So we're going to see that we have another name, or another way of naming ones with transition metals because they have variable charges. With all of these, barium fluoride, we don't have to worry about because barium is always 2+, fluorine is always 1-, so you can only ever make BAF2. That's it. You can't make anything else. But we're going to see iron comes in most commonly these two. And so we're going to have a way of distinguishing between compounds that have iron 2 plus and iron 3 plus. And we would call this the iron 2 ion, where we write in Roman numerals the charge of the ion. This would be iron 3 here. And so, if we take a look at these ugly compounds, ugly because feo, of course, means ugly in Spanish, but anyways, they're also ugly because these are rust compounds, so they're ugly in their own right. So, if we want to think about these, both of these are acceptable compounds. And so we're going to have to figure out what the charge of the ion is within them. So we need to figure out the charge of iron in both of these. And how we do that is we look at the anion. The anion is going to have a fixed charge. So oxygen is 2 minus. That's not going to change. And so by looking at that, we can figure out what the charge is going to be of the iron. So if this oxygen is 2 minus, that means that this iron has to be 2 plus, right? Because they're one of each. That means they have the same charge. So this compound we would call iron 2 oxide. All right, and so if we look at the other one, a little bit more complicated, we know that each oxygen is minus 2. So overall, that's minus 6, or 6 minus, which means that this iron has to be 6 plus. And if there are 2 irons there that are overall 6 plus, that means each iron is 3 plus. Does that make sense? These are already charge balanced for you, so we have to use that to our advantage to figure it out. Notice we could also do the reverse crisscross. Let me write the name out here, but this will be iron 3 oxide. We could do the reverse crisscross with this. If we bring that up, that means we get Fe3 plus and O2 minus. Oops. And that way we can see very clearly it's iron 3. But be careful. Be careful. If you reverse crisscross this one, you get Fe plus and O minus. This is the tricky part about using the crisscross. This is where you have to be careful. We know that oxygen always is minus 2. So we're going to have to make it minus 2 by multiplying its charge by 2, and therefore we would multiply this guy by 2 as well. So just be careful if you're going to use the reverse crisscross on this one. Sometimes, yeah, it'll get you your answer no problem. Sometimes you just have to think as well. So you can't write iron 1 oxide because O minus is not oxide. Oxide is 2 minus. So make sure that you keep that in mind if you're going to use the crisscross. method. All right, so let's do a couple of other ones. And how about I don't know. How about and yeah, let's just work on these two for now. So, if we want to figure out the names of these compounds, we're going to have our options available to us. We could do crisscross, or we could do our kind of algebra method where we kind of just use our least common multiple or whatever, or try and calculate the charge overall. We can do it both ways. We know oxygen is 2 minus. So 2 of those oxygens together is 4 minus, which means titanium would be 4 plus. There is only 1 titanium, so that titanium must be 4 plus. And as a result, we would say titanium 4 oxide. If we were to try and crisscross it, we would have the same kind of problem that we had last time. We would get titanium 2 plus and O minus. So we would need to multiply this by 2, and we would get Ti 4 plus and O2 minus. So we'll get the right answer with crisscrossing, but we just have to be careful. That's the only thing. Alrighty. If we look at the next one, we know chlorate, not perchlorate, sorry, regular chlorate, overall has a charge of -1. If we have 2 of them, that's a charge, that's 2 minus overall. Which means manganese must be overall 2 plus. We have 1 manganese, which means it itself is 2 plus. So we will have manganese 2 chlorate. So you're going to see this is very systematic. It's just practice, practice, practice with these. So with transition metals, we have to figure out what the charge is going to be. We're going to look at this TiO2 one again next week, just because there's something special about that one that may be a little tricky, but we won't worry about that now. I don't want to confuse you guys. Let's do some more. All right. Looking at these. Okay, we see we have nickel and chlorine going on here. We know that chlorine takes a charge of -1, which means overall this is -3 for the 3 chlorines, which means we need +3 for our nickel. There's only 1 nickel, so that nickel must be +3. Nickel 3 chloride. Next one is a trick. Beware. This one we don't have to calculate anything, because zinc does not have a variable charge. as if it were calcium or magnesium or something. Zinc does not need to have a parentheses with a Roman numeral because zinc does not have multiple charges. Zinc is always +2. So note, you would not ever say zinc 2 bicarbonate. You just don't. This is going to be our happy one here. We would not have that here. Much as if we have something like this, we would just say calcium bromide. We do not say calcium 2 bromide. Alright, chemists are very much against having extra information. We don't like redundancy. So calcium is understood that it always has a +2 charge. So we do not ever write calcium 2 bromide. We just say calcium bromide. So it's important again for us to memorize which ions have fixed charges and understand that all the other various metals could have variable ones. So if you memorize that zinc, silver, and cadmium, I'll write them down. Zinc, silver, and cadmium have fixed charges. Just like groups 1 and groups 2 have fixed charges, like sodium is always +1. It's in group 1. Everything in group 1 is +1. These three also have fixed charges, so they're never going to need parentheses for when we name them. All right, but we're going to assume every other transition metal has variable charge. So chromium does these four very often. We have to distinguish these ones by using those Roman numerals. And then this would be chromium 6 down here. I guess what I should kind of finish with is just a reminder of what your Roman numerals are. In case it's been a while, because we don't use these terribly often. This is 1 through 5. We don't really, there's a couple that we see that are above that. We don't typically see 9 and 10, but there they are. So just in case you've forgotten your Roman numerals, that's what those would be. All right, so that's it for today. I'll see you guys on Monday. I'll put up your homework if you want to start taking a crack at it. Just be aware that you're only going to be able to answer ionic compounds right now. We still have non-metal compounds and acids to go. So for right now, you would ignore those. But hooray. Yeah, we're good for now. So enjoy your weekends. Memorizing your polyatomic ions frantically. And yeah, we're good. So I'll post these up for you guys, and then you'll be all set. Don't forget, there are, I think, some lab simulations that are going to be due this weekend, so don't forget about those. And then I think you have the ion electron configuration worksheet that's also going to be due, so don't forget about that one either. All right, sounds good. See you guys later.